So let's welcome Professor Dr. Michael Tarbutt from Imperial College London. And the topic of the talk is testing fundamental physics using laser cold molecules. It's a very interesting one.
Thank you.
Thank you very much.
Yeah, thank you. It's a great pleasure to be here. Thank you for the invitation. So I'll talk about this topic, testing fundamental physics using laser-cooled molecules. And let's just dive straight in here. Does not do anything.
Just click on that PowerPoint. It should do that.
Yeah, and this one was this. Oh, yeah, there we go. All right, so maybe I'll start with just a little bit of general motivation about why we're interested in ultra-cold molecules. I think I'm probably repeating quite a lot of what Simon Cornish told you yesterday, but repeating is not always so bad. Actually, many different reasons why people are interested in molecules at low temperature. The thing that I will mainly talk about is using molecules to test fundamental physics. And people are doing that in many different ways already. For example, using molecules to measure the electron's electric dipole moment and to search for varying fundamental constants. These are actually the two things that I will talk about today. Other people also use molecules to measure parity violation in nuclei and also in chiral molecules, and to search for fifth forces, forces that go beyond the four fundamental forces that we know about. And let me emphasize that actually these tests of fundamental physics using molecules are already being done. All of them are already being done in many different groups around the world, mostly using warm molecules or hot molecules at the moment. But all of those experiments could be greatly improved by cooling the molecules down to low temperature. Another thing that I think is very interesting is studying chemistry in the quantum regime, in a regime where the reactants are under control at the quantum level for all degrees of freedom, including the motional degrees of freedom and orientation of the molecules and so on. And that's not normally what people are doing when they're doing chemistry, but I think looking at chemical reactions in this fully controlled regime, this very fundamental regime, is an interesting thing. Another interesting topic is using molecules to study many-body quantum physics, which I've read about already from Terry this morning, using atoms for many-body quantum physics, and of course you can also use molecules. So the cartoon here is supposed to show a lattice that is filled with polar molecules. And because they're polar molecules, every molecule is interacting with every other molecule through the long-range dipole-dipole interaction. Okay, so this is a strongly interacting many-body quantum system. And if we had it in the lab, we could learn a lot about many-body quantum physics. And then finally, on the list here is using molecules for quantum information processing. The little cartoon here is showing individual molecules that are trapped in tweezer traps. And the rotational states or the hyperfine states of the molecule can act as qubits. These qubits, you can do single qubit operations rapidly using microwave fields or driving two-photon transitions. And you can do two qubit gates between these molecules, again, by using the dipole-dipole interaction between the two molecules. And in fact, everything that I've just said has already been done very recently. And in fact, all of a sudden, this kind of platform of molecules in tweezer traps is suddenly looking like a very interesting platform for doing quantum information processing. All right, so that's kind of an overview, and the things that I will focus on are these top two topics here. I think you would have learned yesterday from Simon about how you can make ultra-cold molecules by assembling ultra-cold atoms into molecules. The thing that I'm going to talk about is a different technique, but we just apply laser cooling directly to the molecules. And I will start by concentrating on these particular species of molecules, calcium monofluoride. The apparatus that we use will, I think, look very familiar to many of you if you've worked on cold atom experiments. It really looks pretty much the same. We make a beam of these calcium fluoride molecules. We do that using cryogenic buffer gas cooling. So we make the calcium fluoride by laser ablation of some precursor target, and those molecules that are born inside this copper cell are cooled to low temperature by helium gas, which has been cooled to 4 Kelvin. And then everything flows out of a hole in the cell and we create the beam. The first thing we do is collimate that molecular beam. Okay, so we have a region here of transverse laser cooling, which removes the transverse velocity distribution. So now we have a very highly collimated molecular beam. We then decelerate that molecular beam down to low velocity using the radiation pressure of this counter-propagating laser light here. And finally, we capture those slow molecules in a magneto-optical trap. So let me immediately show you a little bit of data here. What I'm showing you is the velocity distribution of the molecules as they arrive in the MOT here. The black curve here is the velocity distribution we measure when we just do nothing. Okay, we apply no slowing at all here. It's just what comes out of our cryogenic source. And the red curve is the velocity distribution we measure when we turn on the laser slowing light. And now, of course, you will know this, we have to handle the Doppler shift. There's a Doppler shift between the molecules going one direction and the laser light coming from the other direction. And in this particular experiment, we've tuned the frequencies of the lasers so that the molecules that are resonant with the laser light are the ones that are at this speed here, at about 180 meters per second. And so those are Doppler shifted into resonance with the light. And then you can see that they've been pushed down to about 100 meters per second. You also see that they bunch up at around that speed. And that's because by the time they've moved down to 100 meters per second, they've Doppler shifted out of resonance with the light, and they stop scattering photons, they stop slowing down, and they all pile up at this particular speed. Of course, we need to go to lower speeds than that, and so we now apply a frequency chirp to the laser in order to push the molecules down to lower speeds, and you can see that as we increase the frequency chirp that we apply, we can push them down to lower and lower velocities. Eventually, once they're slow enough, we can capture them in the magneto-optical trap. The MOT for molecules works very much the same as you're used to thinking about for a MOT for atoms. Okay, just that we have to use quite a lot of different lasers here to address many different vibrational branches of the molecule to form a closed optical cooling cycle. Okay, so in fact, we use 4 different laser wavelengths to address the 4 lowest lying vibrational states of the molecule, and that is sufficient to be able to make a MOT. We take pictures of the molecules that are captured in the MOT by imaging their laser-induced fluorescence onto a camera. Here is a picture actually taken on a regular mobile phone camera. We're looking into through the vacuum viewport here. And you see this little glowing orange blob here. This is our MOT of calcium fluoride molecules. We don't normally use a mobile phone camera. We normally use a fancy CCD camera. And so here's pictures on a fancy CCD camera. We measure the temperature of the molecules in the usual way, just by ballistic expansion. So we just turn off the trap and let them expand, and the rate of expansion tells us the temperature. Temperature of the molecules in the MOT is actually quite high, typically a few millikelvin. And so we want to go to much colder temperatures than that. So immediately, as soon as we've captured the molecules in the MOT, we actually immediately transfer them into an optical molasses. And we use the gray molasses cooling method, followed by velocity selective coherent population trapping. And those techniques are actually very efficient at cooling the molecules to low temperature. So when I show you some data of the temperature as a function of time at the very last stages of the cooling process here, and you can see the temperature coming down very rapidly. Eventually we get to a temperature of 5 microkelvin. All right, so all of this we know how to do. So then I come to the applications of these ultracold molecules. And the search one, the first one is using them to search for varying fundamental constants, which actually we just heard about a little bit from Eckhard already. Let me give you a little bit of a motivation here, why we want to do this. First, a bit of theoretical motivation. So theories, or at least some theories, that try to unify gravity with the other forces, so unification theories, some of them predict that the fundamental constants should vary in space or in time. And some theories of dark matter, they predict that the fundamental constants should oscillate in time. And some theories of dark energy, they predict that the fundamental constants should depend on the local matter density. So that if I make a measurement of the constant here on Earth, where the matter density is very high, then I should get one value. And if I make a measurement out in outer space, where the matter density is very low, I might get a different value. That's what these theories predict. And now, actually, if you look at the list here and see what we've got, we've basically got quantum gravity and dark matter and dark energy. And these are some of the biggest problems that we have in fundamental physics, things that we don't understand. And it seems as though this idea of looking for varying constants could shed light on all three of these things. So it seems to be an interesting thing to do. How do you do it? Well, you've seen it already. You measure the transition frequencies in atoms and molecules over a period of time or over a span of space. And as Eckhart told us already, the electronic transitions in the atom, they are sensitive, very sensitive to the fine structure constant, and indeed using atomic clocks, the variation of the fine structure constant is constrained to fantastic precision. You get the fine structure constant from the atoms. The molecules, the vibrational and rotational transitions in molecules, they are sensitive to the electron to proton mass ratio, ME over MP. And this is a sensitivity that you don't get directly from the atoms. And you can get it from the hyperfine structure of atoms, but you don't get it from optical atomic clocks. You do get it from the molecules. Okay? So this is a sensitivity that the molecules have, which the atoms do not directly have, the electron to proton mass ratio. So we would like to make very precise measurements of the variations of this electron to proton mass ratio. And to do that, we need to build a molecule clock, equivalent to an atomic clock, but using molecules. And let me also say that if we do that, then we have a clock. If we have a clock which is based on the vibrational transitions in molecules, this will also serve as a frequency standard in the mid-infrared, which is a part of the electromagnetic spectrum, where at the moment there are no good frequency standards. So we only have these two motivations: testing fundamental physics and also building new kinds of frequency standards. So let me tell you about the system that we have in mind to build here. I think many of you are clock experts, so please, if you think this is insane, please tell me. So the system we have in mind is to use our ultracold calcium fluoride molecules in an optical lattice. Here are some of the relevant energy levels here, showing the vibrational and rotational or hyperfine structure that we care about. What we would like to do is to build a clock that is based on this fundamental vibrational transition of the molecule. Okay? It's a transition of 17.5 terahertz. And we want to measure it by driving this Raman transition here. The vibrational frequency scales as the square root of the electron to proton mass ratio, so that's where we get the sensitivity. And the line width, we don't really know the line width, but we estimate a line width of just a few hertz, so we should make a good clock. The molecules will be in the lattice, which eliminates the Doppler shifts. And now an important idea that in this transition here, the only thing you do in this transition is change the vibrational state of the molecule. Okay, you see, in fact, that if you drive this Raman transition, you do not change the rotation, choose not to change the rotational state of the molecule. In fact, we start here in the lowest rotational state, n equals 0, and we end here in the same lowest rotational state, n equals 0. And now if that's all you do, if all you do in a molecule is change its vibrational state, then hardly any of the properties of the molecule change. And in particular, the magnetic dipole moment of the molecule hardly changes. DC polarizability hardly changes in this vibrational transition. And therefore, the Zeeman shifts and the DC Stark shifts cancel to very high accuracy in this vibration chamber. What's more, we can measure with high accuracy this rotational frequency here. It's a microwave frequency 20.5 gigahertz. And actually this rotational transition is very sensitive to Zeeman shifts and Stark shifts. So we can actually use this transition to tell us what the fields are, the electric fields and magnetic fields in the experiment, and thereby determine the residuals, even in Stark shifts of this clock transition. Okay, so that's what we would like to do. Of course, the molecules are in the lattice, and therefore there will be AC Stark shifts, and the AC Stark shifts do not necessarily cancel perfectly between the two vibrational states. So we would like to find some magic wavelengths where the differential polarizability of the two vibrational levels goes to 0. Here is our calculation of the differential polarizability on this transition here, and you see that there are several places where the polarizability indeed crosses 0. These are the magic wavelengths for this clock transition. And let me point out particularly this magic wavelength out here, where the differential polarizability crosses 0 at a very shallow angle. And so we think actually this would make a very nice magic lattice wavelength. This is our estimate of what we think the fractional instability of such a clock will be as a function of the averaging time. And you see that on a reasonable kind of averaging time, we expect to be able to reach something like a part in 10 to the 17. And we've also made an effort to try to evaluate what we think the systematic uncertainties would be for such a clock transition based on some kind of reasonable laboratory conditions here. So I won't go through the table in detail, but the bottom line is that for some relatively easy conditions to achieve, we think we should get an accuracy again of about a part in 10 to the 17. Okay, so for this we need our molecules in an optical lattice. So far I showed you the molecules in a MOT, in a lattice. And so we've started out just with a simple lattice at 1064 nanometers. Well, we have 50 watts available. This is not quite a perfect magic lattice at the moment. We start with 1064 nanometers and then later on to the magic lattice. Okay, so we have this 50-watt laser light. We retroreflected to make a 1D optical lattice here, and here is a picture showing molecules that are trapped in this 1D optical lattice. In this case, there's about 500 molecules in this lattice, not so many right now, at a temperature of 50 microkelvin. The lifetime in the lattice is about 1.7 seconds, and the density of the molecules here is about 4 times 10 to the 9. So we're working hard right now to try to increase the number of molecules that we can couple into the lattice. We've also been learning how to drive coherent oscillations, coherent transitions in the molecules while they're trapped in the lattice. Okay, so here we're driving Rabi oscillations, seeing Rabi oscillations on the rotational transition of the molecule for molecules that are confined in the lattice. Okay, you see these nice Rabi oscillations on this microwave transition. So we can already do that on the rotational transition of the molecule. Of course, what we really want to do is to do it on the vibrational transition of the molecule we're now working. I just flash up because I told you already that to drive this clock transition, we want to drive a 2-photon Raman transition. And that's really what we want to do. But actually, we've also been having fun driving 1-photon vibrational transition of the molecule. So I just flash this up for you. And so we just drive directly this vibrational transition here, which is a transition at 17.5 terahertz. And we do that with a very unusual laser source. It's a quantum cascade laser operating in this mid-infrared region. And indeed, we're able to drive these single photon transitions directly in the molecule. You'll see here is the hyperfine structure of this vibrational transition. And actually, all of this we have to do with this quantum cascade laser in the mid-infrared, where we have to calibrate the frequency of the laser. We do that with absorption spectroscopy of N2O. And so this is our absorption spectrum of the N2O molecule. N2O is laughing gas. Okay, so you can actually pick up on the street corner. You move in the right circles, maybe move in the wrong circle. Anyways, I just flashed this up because we've been having fun doing this. What we really want to do is drive these two photon vibrational transitions. And what we have in mind is to drive this Raman transition with an up leg at 1064 nanometers, a down leg at 1134 nanometer. The 1064 nanometer laser is already the lattice laser, so that we've now added this 1134 nanometer laser. Of course, these lasers have all to be stabilized to provide narrow line widths. And we have now in the lab an ultra-stable cavity with a finesse of 300,000. And I've just completed the work to do the PDH locks of the two lasers to this ultra-stable cavity. All of that is working. We're kind of gearing up now to try and drive this, Raman transition for the first time. Okay, so that's where we are on that project, and actually looking a little bit further ahead to where we would like to go. Of course, what we really want to do is compare two different types of clock. So what we have in mind is to compare our molecular clock, which is sensitive to the electron to proton mass ratio, to an optical atomic clock, for instance, a strontium lattice clock, which is not sensitive to the electron to proton mass ratio. Okay, and then take the frequency ratio between those two clocks and look to see whether that is changing in time. And that's in fact the way you get access to variations in the fundamental constants. And that we would like to do by comparing our molecular clock at Imperial College in London to a strontium lattice clock at MPL, which is possible through a dark fiber link with frequency codes at the two ends. All right, so then let me turn to a second application of these molecules, which is measuring the electron's electric dipole moment using molecules. And again, let me start here with a little bit of motivation why we're interested in doing this. So the first thing to say is that the existence of a permanent electric dipole moment violates time reversal symmetry, which already makes it interesting. So here I have a little cartoon which is supposed to show an electron or any fundamental particle. In fact, it has a spin, which is denoted by the red arrow here. The spin is pointing up. And this particle also has a permanent electric dipole moment. An electric dipole moment is a distortion of the charge distribution away from the spherical distribution. So here my electron has a little bit of excess positive charge near the bottom and a bit of excess negative charge at the top. So it has an electric dipole moment. Also pointing up. And now if we apply the time reversal operator to this system, okay, so time reversal, that just means play the movie backwards. Okay, so if you have a spin which is going around in one direction, now you play the movie backwards, the spin is going around in the opposite direction, so the spin is now going downwards. But the electric dipole moment, that's just a static distribution of charge. Okay, it doesn't care about the direction of time, and so it's still pointing up. And what you see is that these two electrons are not the same as each other. So if time reversal symmetry is a symmetry of nature, then these two electrons also ought to exist in the universe on an equal footing. Another way to say the same thing is that the electron ought to have two internal degrees of freedom. Okay, so the spin and the direction of the electric dipole moment relative to the spin. You have two internal degrees of freedom. But actually, we know for sure that the electron has only one internal degree of freedom. And if it had two, then you have to completely rebuild the periodic table, and the whole chemistry is different. So the conclusion is that one of these electrons just doesn't exist, which means that either the electric dipole moment is identically zero, in which case there's no problem here, or time reversal symmetry is not a symmetry of nature. So that's already an interesting thing to try to find out, of course. And also, time reversal violation is actually connected to the other discrete symmetries of nature. And it's connected through this theorem, the CPT theorem, which is a mathematical fact concerning Lorentz invariant quantum field theories. It states that all Lorentz invariant quantum field theories are invariant under this combined symmetry, CPT. C is charge conjugation, P is parity, and T is time reversal. Of course, this also has to be checked to find out whether this is correct. It's a mathematical fact about Lorentz invariant quantum field theory, not necessarily about nature. Okay, and I think we will probably hear about Stefan from Stefan about how you could test whether this CPT invariance hold or not. If we assume that it does hold, then T violation is exactly equivalent to CP violation. And CP violation is especially important because it's one of the ingredients that we need to understand the existence of matter in the universe. So, you know, when you look out into the universe, all you ever see is matter. You don't see any antimatter anywhere. Unless you go to Stefan's lab at CERN, you don't find any antimatter anywhere in the universe. And this, you know, great imbalance between matter and antimatter, we don't understand that. So the current theories that we have do not explain this asymmetry between matter and antimatter in the universe. What we do know is that a necessary ingredient to generate this imbalance is CP violation. So you see how all of these things are connected to each other. So this is an interesting thing to measure, and also interesting to ask, well, what does theory say about this quantity, the electron's electric dipole moment? And the answer is, well, it depends what theory you look at. Okay, so here's a plot showing the predicted value of the electron's electric dipole moment. In the units that we always use, it's an electric charge times a centimeter. And what you see is that the standard model of particle physics, it actually predicts a non-zero value for the electron EDM, but an incredibly tiny value. It's somewhere down here at 10 to the minus 38 centimeter. All these other blocks of color here, they're the predictions of other theories that extend the standard model. And you see that quite generically, they tend to predict values for the electron EDM that are some 10 orders of magnitude larger than in the standard model. So for example, this green box here, this is the predictions from the minimal supersymmetric standard model extension, where CP violating phases of order 1. The blue box here are predictions of other kinds of supersymmetry. And the dashed line here is actually the current experimental limit, which comes from a really wonderful, very beautiful experiment I've done at Gila using hafnium fluoride molecular ions. And what they found was a value that is consistent with 0, meaning that everything that is above this dashed line is now ruled out by this experiment. And so you can see that these EDM experiments have really tremendous power in testing physics beyond the standard model. So how do you do it? How do you measure the electron EDM? Well, the principle is actually very simple. So here I have another cartoon that shows, let's say it's an electron, which is processing in a magnetic field. And so the electron has a spin. Associated with the spin, it has a magnetic dipole moment. We put the system in an applied magnetic field, and there's an interaction between the magnetic dipole moment and the applied magnetic field. That applies a torque, which causes the spin to precess. So you all know this, particle precessing the magnetic field. If now, in addition to the applied magnetic field, we add an electric field, and let's say it's parallel to the magnetic field, now there's an additional interaction. It's the interaction between the electric dipole moment and the applied electric field. And that additional interaction causes an additional torque, which causes the spin precession frequency to change. In my cartoon here, it got a little bit faster when I added the electric field. And conversely, if I put the electric field in the opposite direction, then the torque is in the opposite direction. The precession frequency will slow down. Okay, so all you have to do to measure the EDM of the electron is to measure the change in the precession rate when the electric field direction is reversed. That's the whole experiment. Almost all of the modern experiments that try to measure this use the electrons that are bound up inside a polar molecule. So it turns out that the sensitivity of the experiment is enhanced enormously when your electron is like the valence electron of a heavy polar molecule. And the picture here is try and show you what happens. So you have a molecule, it's a polar molecule. You apply an electric field in the lab, a fairly modest electric field, which aligns the molecule some direction in the lab. And now, the valence electron in this molecule is seeing the applied electric field, but also the internal electric field of the molecule. And that internal electric field of the molecule is absolutely enormous, and vastly larger than the electric field that you actually apply in the lab. So that's a very, very simplified picture of what happens. In more detail, it's actually a relativistic enhancement that you get here. And so you get it particularly when you have heavy polar molecules. That's what everybody likes to use. So as an example of what we think is achievable using ultracold molecules, here again, I have a kind of vision of an experiment that is done with ytterbium fluoride molecules. Okay, so far I spoke about calcium fluoride. The calcium fluoride is too light. We need these heavy molecules, and the calcium fluoride is too light to be particularly sensitive to the electron EDM. We want to go to much heavier species, so we like to use these ytterbium fluoride molecules. If we had 10 to the 4 of them in an optical lattice with a spin precession time in the lattice of about 4 seconds, then you can easily work out that the statistical sensitivity of such an experiment will be sitting at this level here. That's where we would like to go. Okay, so in my lab at Imperial College, we're actually building 2 separate experiments to do this, to measure the electron's electric dipole moment using ultra-cold ytterbium fluoride. And I'll show you here the first experiment, which is actually a beam experiment. So the molecules are not trapped in a lattice, they're moving in a molecular beam. It looks somewhat similar to the things I've already shown you here. We make a beam of ytterbium fluoride using this cryogenic buffer gas cooling method. We then collimate the molecular beam in the 2 transverse directions using this 2D optical molasses. And that's really the key advance here, that we're able to cool these molecules down to low temperature in the transverse directions. That means they're basically no longer have any velocity in the transverse direction, so they're extremely highly collimated. And that means that they can travel for a very long time without any significant expansion of the beam. Show you some, before I say about the rest of the experiment, I'll just show you some pictures here to show that the laser cooling of these ytterbium fluoride molecules works. So what I'm showing you is the density distribution of the molecular beam measured at the end of the beam line here. So it's not shown on the picture. There's actually a camera right at the end of the beam line that looks down the beam line. Yeah, and then we use a pair of probe lasers that cross at 90 degrees right at the end of the beam line here. Measure the density distribution of the molecular beam by laser-induced fluorescence detection. In this picture here, we're not applying any cooling at all. Okay, so the molecular beam is just huge by the time it gets to the end of the beam line here, fills the entire screen here. And all we see, we have these cross probe beams, so we see laser-induced fluorescence where the probe beams are. And we just see the cross of the probe beams. And now we turn on the cooling. First of all, we do it in 1 dimension. And you can see on the camera this bright stripe appearing here, which is due to molecules that have been cooled in that direction, in the horizontal direction too. And then we apply it in both directions. You can see this very, very bright spot appearing in the center of the camera here. This corresponds to an extremely well collimated molecular beam. So we have about 1 million ultracold molecules per shot in the experiment, and actually the laser cooling has increased the brightness of the beam by a factor of 300 in this case. All right, so these collimated molecules, they now pass through the rest of the experiment here, which I'll tell you a little bit about. First of all, they pass through this optical pumping region, which just transfers the molecules to the ground state that we're interested in using. And then the molecular beam passes into this magnetically shielded region, where we apply a very, very small and well-controlled magnetic field and quite a large electric field. They pass through this first pair of lasers here, when we prepare the spin of the molecules. And so we actually prepare the spin using stimulated Raman adiabatic passage. We upshot stirrup, when they pass through the stirrup lasers. The upshot is the spin is now pointing in the horizontal direction, in the direction that we know. And then the molecules fly freely for a while in this combined magnetic and electric field, and the spin processes around. And then they pass through the second region of stimulated Raman in adiabatic passage. If the spin is still pointing along the original direction, then this second stirrup here transfers the molecules to one particular hyperfine state of the molecule. And if the spin is processed around by 90 degrees, the stirrup transfers the population to a different hyperfine state of the molecule. And so we map the direction of the spin onto two different hyperfine states of the molecule, and then finally we just detect the populations in each of those two hyperfine states. So in the end, the signal in the experiment is just the population difference between the two hyperfine states, which is a direct measure of the spin precession angle. The population difference is just the cosine of the spin precession. So here, I'll show you some actually new data. I'm actually the first people outside of our team to see this data. So it's actually showing the first interference fringes from this new experiment, where we indeed measure what we call the asymmetry. It's the difference in population between these two hyperfine states at the end of the experiment, as a function of the applied magnetic field. And as you change the magnetic field, then you change the spin precession angle, and therefore you change the spin. As you change the magnetic field, you change the spin precession frequency, and therefore you change the spin precession angle after a fixed time. And we're just mapping out that angle as a function of the magnetic field. You see these cosine fringes at the output of the experiment. In fact, there are two data sets here. A red one where the electric field is in one direction, and a blue one where the electric field is in the opposite direction. So this is in fact our very first measurement of the electron EM using these ultracold YBF molecules. Not a very precise measurement yet. We have many, many things that have to be improved upon, but everything in the experiment is now working. There are many, many challenges that have to do with the spin precession region. Mostly it has to do with controlling magnetic fields. And I think I'm probably running out of time, and you don't really need to know about my nightmares. So I will not go into my nightmares or indeed the solutions to my nightmares. Let me just skip here to the end and tell you about a second experiment that we're developing now in the lab. Looking a bit further to the future. So with this beam experiment, it's working, and we have a lot of work still to do, but everything is working. We plan to make a new EDM measurement with this apparatus. Looking further to the future, what we really would like to do is not have a beam, but have our YBF molecules in an optical lattice and do the measurement in the lattice. Gearing up to try to do that is very, very challenging. So the apparatus is basically the same as I showed you for the calcium fluoride. We try to put these molecules in a magneto-optical trap and then transfer them into an optical lattice where we do the experiment. The laser cooling of the YBF is much, much more difficult than the calcium fluoride. It's in part just that the molecules are heavier. They have a lot more momentum, which makes it more difficult to push them around with photons. And it's also in part that the branching ratios, the vibrational branching ratios for this molecule are not as favorable as for the calcium fluoride. Okay, so it's quite difficult, but we're working hard to do this. One thing that we really wanted to get right is to actually have a very, very slow molecular beam from the outset. And because the molecules are so difficult to slow down, we wanted to start with a very, very low velocity. And so we've been developing better cryogenic buffer gas sources that produce very slow molecules. And again, I won't go into all the details here, but the upshot is that we have this blue velocity distribution here, which is actually producing molecules out of this source with a substantial flux all the way down to about 30 meters per second. And that's really slow. That helps us a lot. And the second thing I want to show is some pretty new data showing that indeed we are able to decelerate these molecules using the radiation pressure of this counter-propagating beam here. And so what I'm showing you is the change in the velocity as a function of the time that we apply this slowing laser. You can see the molecule's getting slower. A relatively modest change in the velocity so far, but we're starting from quite slow speed, so we don't have actually too much further to go. All right, so that's what I wanted to tell you about. Let me thank the current group members who are working on these experiments. A highlight here that we have some postdoc positions available in the group, so if you're interested, please come and talk to me. And finally, let me just flash up that the International Conference on Atomic Physics will be held at Imperial College in London in the middle of July this year, and registration has just opened. This is a very, very exciting and wonderful conference series, and we're really honored to be hosting it. Hopefully many of you will choose to come. Thank you very much.
Thank you for this interesting talk. And we have time for a few questions before we go for lunch.
Yeah, maybe this question, but when you consider the electron in the electric field, the question is how is the electron can stay in non-zero electric field, because it's should be stabilized by electric field, or you need some time-dependent electric field, so the electron just have no time to react.
No, it's a very good question, and indeed it was a question right from the very beginning of this field. Okay, so the question is, yeah, why is the electron in any net electric field at all? Why doesn't it just move to the place where the electric field is zero? And in fact, in the non-relativistic limit, that's precisely what it does. Okay, so if you take an atom and you apply an electric field to the atom polarizes in exactly the right way to make sure that the net electric field on every electron is zero. So that's right in the non-relativistic limit. The relativistic, through relativity, it's no longer right, because we have in a simple picture, you have the addition magnetic forces. And magnetic forces can balance the electric forces and leave you with a net electric field. And that is in fact what happens, and ultimately is responsible for this enhancement of the electric field rather than suppression.
With your calcium chloride molecular plot, you said that the variation of the dipole moment, the molecular dipole moment and magnetic moment would be more or less neglected with vibrational transition. I can understand why that would be the case for the magnetic moment, but less so for the electric dipole moment of the molecule, because the average bond length is going to increase with vibrational excitation. And I guess, if you think of this as a calcium plus chlorine minus, then you would expect the dipole moment to increase on vibrational excitation. But has that been measured, the stark effect on that vibrational transition?
Yeah, that's a very good question. But I think the dipole moments are known for both the lowest vibrational state and the first vibrational state, and they are very, very similar to each other. And so I buy your picture that actually, as you incite the thing, the bond should stretch. But I think actually right down at the bottom of the potential curve, where everything is harmonic, it really doesn't. The mean is sort of staying in the same place. Yeah.
In your calcium fluoride mod, so when you put your atoms in lattice, you mentioned 50 microfarad, while your mod is at 5 microfarad. So are you experiencing some heating because it's 10,064 nanometer later?
I don't think we're limited to 50 microkelvin because of some lattice heating. We have seen lattice heating, which is limited the lifetime. I think we've solved that. I think it's really that that we get to the 5 microkelvin by exploiting so we use velocity selective coherent population trapping. It requires coherent dark states in the system, and the coherent dark states are destabilized by the AC stark shifts of the lattice light. I think that's what happens. And so this cooling scheme, which relies on the presence of robust dark states, fails in the presence of these AC Stark shifts because we no longer have the robust dark states. I think that's what happens.
Okay, so if we have no more questions, let's thank once again